In our next part in the topic of nitrogen, we have the ammonia. And the ammonia, after the nitrogen gas, we need to know the test for it. How can I know that this colorless gas that I have is ammonia? How can I test for it? How can I collect it the same way I have collected nitrogen or not? How can I dry it? How make it ammonia, which is just gas without any water vapor or water traces in it? And how can I manufacturally, industrially produce it by the Haber process? The first thing that we will take is a test for the nitrogen. No, it's not nitrogen this time, it's ammonia. So the test for ammonia is that the first thing, it's not a test, we just a smell of the ammonia. We know that the ammonia has a pungent smell. So the name of ammonia smell is pungent. It is a very strong and penetrating smell. It's not a bad smell, it's a penetrating smell that even in the old times they use when there is somebody who is unconscious, they will use some of the they will use some of the ammonia so that it helps this guy to wake up. It's not the strong unconsciousness that lasts for months and years and days. This is like a mild one only. The most famous test is for the ammonia because it has a basic character. So because ammonia is basic, it's expected to change the color of any litmus paper which is damp from red to blue. So if you brought a litmus paper which is red and then you make it damp, because this test will not work if it's not damp. It's wetted with water, a little bit wetted, not soaked in water, a little bit wetted with water, and then you place it in the test tube which has the gas, the ammonia gas. You'll see that it starts to get blue at the ends, and then all of it will change. The place which is affected by that is going to change into blue. This is because the ammonia gas is a weak base, so it changes from the red litmus paper into the blue color by the ammonia gas. The next thing that we'll take about the gas of ammonia is its collection. How can I collect the ammonia gas? You'll see the four methods that we have taken is the collection over water. I cannot collect it over water because it is water soluble. If my gas is water soluble, it cannot be collected over water. What about the gas syringe? This is always a very good method that in the exam, if you want to collect any gas, the gas syringe will be the best method always. It's good because it doesn't only help you in the gas collection, it helps also in measuring its quantity. How much is the volume of this gas we can see from the gas syringe. Another method for the collection is it the downward delivery or the upward delivery? The density of ammonia gas is very low, so it can be collected also by the upward delivery. This is because it is less dense than the air, so the air will be collected. The air will go down in the place where I'm collecting it, and the gas will come up, so ammonia is less dense, so it will be up. When this upward delivery, the gas is produced here, it comes here into this in the small delivery tube and it goes up, so it will be collected and comes up here because it is less dense than the air. I can still collect it over water only if it's not required dry. If it's ammonia solution and I don't care if it's dry or not, then I'm going to use the ammonia collection over water. The drying method depends on if the substance that I'm using is reactive with the ammonia or no. So I can use calcium oxide because calcium oxide will not react with it, and then it will this is the drying agent that will collect the calcium oxide. I cannot use sulfuric acid because sulfuric acid is an acid that will react with this base. So calcium oxide, if you note it, is a base, so it will not react with this base, and sulfuric acid is an acid, so it will react with the ammonia, so it will not be good for drying agent. I cannot use also calcium chloride because calcium chloride is gonna react with it, so I cannot use it as a dry agent. So don't use the sulfuric acid or the calcium chloride, just use the calcium oxide as a drying agent. Now let's look about the next part, which is industrial manufacture of ammonia. How can I use the Haber process to produce ammonia? This process was firstly known because it reacts with the famous reaction nitrogen and hydrogen forms ammonia, so it was well-known reaction, but the conditions of the reaction is what's adjusted by Fritz Haber. This is the German scientist, both loved and hated at the same time. He did some great things, that's why he was loved and took the Nobel Prize, but then after that he made a lot of bad things in the World War II that's too much hated afterwards. So the nitrogen reacts with the hydrogen gas, both of them gases to form the ammonia gas in a reaction which is very well known to be a reversible reaction. How I'm going to adjust the conditions of this reaction to make this reaction give me the most possible content of ammonia and give me very few of the nitrogen and the hydrogen. This is what we are going to say. Well, we know that ammonia can be produced from nitrogen and hydrogen, but the problem is that this reaction happens in both directions. So sometimes it favors the going towards the ammonia and sometimes favors going towards nitrogen and hydrogen. But since our important yield is the ammonia gas, this is what's known as the yield. The yield is always the production of a higher quantity or concentration of the product in focus. So I need to produce more ammonia than going to the backward direction. So I need my reaction to be always in the forward direction more than it is in the backward direction. So I need to force the equilibrium to move to the forward more than to the backward. Let's see first what are the nitrogen and hydrogen sources that I can use to produce the ammonia. We just explained that the source of nitrogen is industrial by the fractional distillation of the liquefied air. So I have big resources of air, and I can produce by the fractional distillation, the nitrogen gas. But what about the hydrogen? There are two main sources that I can get the hydrogen. The most famous one is that I can make catalytic cracking, so thermal catalytic cracking of long chain hydrocarbons, big carbon compounds that contain carbon and hydrogens called hydrocarbons, and they are full of hydrogens and carbon. So when I break them, usually a side product that's produced is hydrogen. So I can take this hydrogen which I brought from the catalytic cracking of the hydrocarbons together with the nitrogen and put them in the same container so that they can react and form the ammonia that I want. So we must know the conditions that this reaction happens at. It happens, you have to memorize the numbers. 450 degrees Celsius, 200 atmospheric pressure, can use a catalyst to make the reaction faster. Since you said that the catalyst cannot make any effect on the equilibrium, I'll just make it reach the equilibrium fast. It can use the iron, which is finally divided. Because it's finally divided, it has a big surface area, and we know the surface area increases the rate of the reaction. As we explained, nitrogen reacts with hydrogen. The balance is N2 and H2 forms 2NH3. This is a finely divided iron 450 degrees and 200 atmospheric pressure. The reaction is exothermic, and we will take very important note of this because it will help us in the equilibrium balance. Still, after all of that, the yield is very less. So I get only 30% of the product as ammonia, and the rest is still nitrogen and hydrogen. So what I'm gonna do, I'm gonna recycle this. So what you will do with the byproducts that's not benefit from, they are going to be recycled, go in the process again, then produces ammonia again. I'll still do this until I get almost 80 something or 90% yield of ammonia. So I get to about 80% or 85% yield of ammonia, which is a very high concentration. Now let's see how can we play with the conditions and what did Haber exactly did. When Haber increased the pressure, he found that increasing pressure to a certain limit, which does not make the devices break, is going to make the equilibrium system tries to reduce the pressure. So when the system tries to reduce the pressure, it moves to the direction of less moles. And this less moles is found on the forward direction because there are 2 moles here or 4 moles here. So it moves mainly towards the forward than the backward direction. This is where the yield is of ammonia, so this increases the yield. At the same time, if he tried to decrease the pressure, then the pressure is going to be increased, which moves to the backward direction. So I don't want this option. I will use only option number A, which is increasing the yield, not B. What about the temperature? If you increase the temperature, so in option number C, I will have to increase the temperature so that I keep the rate of the reaction high. It's a high rate of the reaction. But the problem is that doing that will make the reaction go to the endothermic direction, which is the backward direction. Since the exothermic is forward, we tell the reaction is forward, so the backward is the endothermic, and this reaction is badly going to the backward direction, which is not good because I needed to go forward. So I have a higher rate but less yield. And at the same time, the other option is option D. I will decrease the temperature, which will give me a very good yield because the reaction will try to increase it so it moves to the exothermic forward direction. So there is more yield, but the problem is that the rate of the reaction is very low. And money-wise, financially-wise, I don't want a low rate. Any production manager knows that a high rate, business-wise and money-wise, is much more important than the high yield. So again, a choice between rate and yield will always favor the rate over yield. If you are having a planet which makes so if you have a factory that you want to produce iPhone mobiles in, and you want to choose between making a very large number, let's say 1 million iPhones given in a 6 month time versus 100,000 given in 1 week. Which one you are going to choose? Or let's say 10,000 only, so I'll make it not very greedy. So I'll choose 10,000 in 1 week. Which one you are going to choose? Financially, choosing a higher rate of production over a higher yield of production is much worthy because you don't know what happens after 6 months. Maybe nobody wants to buy the iPhones for any reason. So what you will do with this 1 million mobiles? It's very important to have the 10,000 in your monies after selling them in your pocket, so you can use them as money that will help you increase your production and do things in your factory. The same thing is going to happen for the scientist who chooses the rate of the reaction over the reaction yield. So the options that he is going to choose high pressure that causes the system to decrease the pressure so it moves to less moles, which is a higher yield. And the other option is to use a high temperature, which although it has a low yield, but it has a higher rate. So this is option A and C. You will never use option B because option B gives you a low pressure and a high pressure, and high pressure goes towards the back side. You decrease the pressure, so it increases the pressure. Always differentiate between what did you do, so your action and the response of the system. System tries to restore the equilibrium, differentiate between these two. What I did is increase, what the system responded is by decrease. Here, what I did is decrease, the system responded by increasing, moving towards more mole, which is backward, which is not good. While the temperature, if you decrease the temperature, it will be bad for the yield, bad for the rate of the reaction. Although it's good for the yield, but I don't choose this one. This is not good. I prefer to get higher rate with less yield. If somebody asked you how you can recycle the gases not producing ammonia, I will recycle them by cooling. So I will recycle them by cooling the mixture so I can separate the nitrogen and hydrogen away from the ammonia. And then according to that, I can start making it into the reaction again and producing again more amount of the gas ammonia. If you want to produce the ammonia in the lab instead of producing it in industry, then just react some of the NH4Cl ammonium chloride together with the calcium hydroxide. This will produce for you the ammonia gas, 2 moles of ammonia gas plus calcium chloride and water. This is only to make it on a small scale in the lab.